Hello, everyone, and welcome back to another journey into the mysteries of science. Wherever you find yourself this evening, I hope you're comfortable and ready to let your mind wander through some of the most fascinating corners of our universe. If you enjoy these gentle dives into the wonders of science and would like to hear more, giving this video a thumbs up really helps the channel grow. And for those of you who've already subscribed, thank you so much. Your support truly means everything. So let's begin, shall we? Tonight we're exploring the most intriguing facts about quantum physics, that strange and beautiful branch of science that reveals just how peculiar our universe really is when you look closely enough. And trust me, it's far more extraordinary than you might imagine. The world around us appears solid and predictable. When you drop your keys, they fall to the floor. When you flip a light switch, the bulb illuminates. When you close your eyes, the moon doesn't simply vanish from existence. These everyday experiences feel reliable, governed by laws that make perfect sense. But in the early decades of the 20th century, scientists began peering deeper into the fabric of reality itself. And what they discovered challenged everything we thought we knew about how the universe operates. They found that light, which we'd always understood as waves, could sometimes behave like individual particles. Even stranger, tiny particles of matter could act like waves, spreading out across space in ways that defied all logic. Most unsettling of all, the very act of looking at something didn't just reveal what was already there. It actually seemed to change the outcome entirely. This wasn't the result of faulty equipment or sloppy measurements. These discoveries were real, reproducible, and absolutely revolutionary. They gave birth to quantum physics, a completely new way of understanding reality, where certainty gives way to probability, where cause and effect become beautifully blurred, and where the universe reveals itself to be far stranger and more wonderful than anyone had dared to imagine. Here's our first fascinating fact about the quantum world. At the smallest scales imaginable, energy doesn't flow smoothly like water from a tap. Instead, it comes in tiny, discrete packets called quanta. This discovery emerged from a rather mundane problem that had been puzzling physicists for years. When you heat up a piece of metal, it glows, first red, then orange, then brilliant white as the temperature increases. This seemed simple enough to explain, but the mathematics kept producing impossible results. According to the equations of the time, a heated object should emit infinite amounts of energy at certain frequencies, which was clearly ridiculous. The prediction was so absurd that scientists nicknamed it the ultraviolet catastrophe. Enter Max Planck, a careful and conservative German physicist who wasn't looking to revolutionize anything. He simply wanted to fix the broken mathematics. Planck proposed something radical. What if energy couldn't be emitted in just any amount? What if it had to come in specific, indivisible chunks, like coins that you can't split in half? He called these packets quanta and introduced a tiny constant to describe their size. When he plugged this idea into his equations, something magical happened. The infinite energy problem vanished completely, and the math finally matched what scientists observed in their laboratories. Planck himself didn't quite believe his own solution. He thought of it as a mathematical trick rather than a description of how nature actually worked. But his insight laid the foundation for everything that followed, revealing that even something as basic as energy has a granular, discrete structure at its deepest level. Our second remarkable fact involves one of the most famous scientists in history, and a mystery that seemed almost too strange to be true. Albert Einstein, building on Planck's work, tackled another puzzling phenomenon called the photoelectric effect. When light shines on certain metals, it can knock electrons loose from the surface. This made sense in principle, but the details were baffling. According to the wave theory of light, brighter illumination should always produce more energetic electrons. But experiments showed something completely different. The brightness of the light didn't matter nearly as much as its color. Dim blue light could easily eject electrons, while even the brightest red light sometimes couldn't budge them at all. There seemed to be a sharp threshold that made no sense under the existing theories. Einstein proposed something audacious. What if light wasn't just a wave, but could also behave like a stream of particles? He suggested that light came in individual packets of energy, later called photons, each carrying a specific amount based on the light's frequency. If a single photon had enough energy, it could knock an electron free. If not, even billions of photons couldn't do the job. This idea of wave-particle duality became one of the cornerstones of quantum physics. Light could be a wave when it needed to be, spreading out and creating interference patterns, but it could also act like particles, colliding with electrons one by one. The universe, it seemed, wasn't interested in fitting into our tidy categories of either this or that. Einstein's explanation was so groundbreaking that he received the Nobel Prize in Physics for it, not for his famous theory of relativity, as many people assume, but for solving the mystery of the photoelectric effect. Yet even Einstein found the implications of quantum physics deeply troubling. He would later spend decades trying to prove that the quantum world couldn't be as strange as it appears perhaps to be. Here the most mind-bending fact of all, one that continues to puzzle scientists and philosophers to this day. In the quantum realm, particles don't seem to have definite properties until someone looks at them. This isn't a poetic metaphor. It's a measurable reality that's been confirmed in countless experiments. Consider the famous double-slit experiment, which sounds deceptively simple. You shine light through two narrow openings in a barrier and observe the pattern it creates on a screen behind them. If light were made of particles, you'd expect to see two bright stripes corresponding to the slits. But instead, you see a series of alternating light and dark bands, an interference pattern that can only be created by waves overlapping and canceling each other out. The truly bizarre part comes when you dim the light source until only one photon passes through at a time. Logic suggests these individual particles should behave like tiny bullets, each going through one slit or the other. But even single photons, arriving one by one, gradually build up the same wave-like interference pattern. It's as if each particle somehow goes through both slits simultaneously and interferes with itself. But here's where it gets even stranger. The moment you try to peek and see which slit each photon actually uses, the interference pattern vanishes completely. The photons suddenly start acting like ordinary particles again, creating two simple stripes instead of the complex possibility wave pattern. It's as if the mere of being observed forces the quantum system to choose a single, definite behavior. This phenomenon suggests something profound about the nature of reality itself. At the quantum level, particles exist in what scientists call superposition, a ghostly blend of all possible states simultaneously. Only when a measurement is made does this cloud of possibilities collapse into a single, concrete outcome. The implications are staggering. Means that asking it where a particle was before you measured it might not even be a meaningful question. The particle wasn't anywhere in particular. It was everywhere it could possibly be, all at once. Reality, at its most fundamental level, appears to be made not of definite things, but of shimmering probabilities that crystallize into existence only when observed. This strange relationship between observation and reality has spawned countless philosophical debates. Some interpretations suggest that consciousness itself plays a special role in shaping the universe. Others propose that every possible outcome actually occurs, but in separate parallel realities that branch off from each other like an infinite tree of possibilities. What makes these quantum effects even more remarkable is their incredible precision. While the behavior seems random and unpredictable, the probabilities follow mathematical laws with extraordinary accuracy. Scientists can how likely predict exactly outcome will each if they be, even can't say which specific result will occur in any given instance. These aren't just abstract curiosities confined to physics laboratories. The same quantum principles that govern individual photons and electrons also underlie the technology that powers our modern world. The computer or phone you're using to watch this video depends on quantum mechanics to function. The GPS satellites that help you navigate rely on quantum effects to maintain their accuracy. Even more exotic applications are emerging. Scientists are developing quantum computers that could solve certain problems exponentially faster than conventional machines by harnessing the power of superposition and other quantum phenomena. They're also working on quantum communication systems that would be absolutely secure, guaranteed by the laws of physics themselves. As we continue our journey through the quantum wonderland, we'll discover even more surprising facts about how the universe really works at its deepest level. We'll explore particles that can tunnel through solid barriers, pairs of particles that remain mysteriously connected across vast distances, and the strange truth that even empty space isn't truly empty at all. But for now, as you settle deeper into comfort, perhaps it's enough to marvel at this first glimpse behind the curtain of reality. The universe, it turns out, is far more magical and mysterious than our everyday experience suggests, and we're only just beginning to uncover its secrets. Let me continue exploring the most fascinating facts about quantum physics, each one more intriguing than the last. Our next extraordinary fact reveals something that would make even the most imaginative storyteller pause in wonder. In the quantum world, particles can accomplish what seems utterly impossible. They can pass through walls that should completely stop them. This phenomenon, known as quantum tunneling, happens because particles at the smallest scales don't behave like the solid objects we encounter in daily life. Picture trying to roll a ball up and over a hill. In our familiar world, if the ball doesn't have enough energy to reach the top, it simply rolls back down. But quantum particles play by different rules entirely. Even when they lack the energy to climb over a barrier, there's always a chance they might appear on the other side, as if they've somehow slipped through solid matter without breaking it. This isn't magic or science fiction. It's a measurable effect that occurs because particles exist as probability waves rather than discrete points. These waves can extend beyond barriers, creating a small but real possibility that the particle will be found on the far side. The taller and wider the barrier, the less likely tunneling becomes, but it never disappears entirely. Quantum tunneling is responsible for some of the most fundamental processes in our universe. Deep within stars, hydrogen nuclei don't actually have enough energy to overcome their mutual electrical repulsion and fuse together. According to classical physics, stars shouldn't be able to shine, yet they do, precisely because quantum tunneling allows these nuclei to occasionally slip past their energy barriers and merge, releasing the light and heat that make life possible. This same principle operates in the radioactive decay that powers geological processes and helps scientists date ancient artifacts. Particles trapped inside atomic nuclei can tunnel out, even when they don't have sufficient energy to escape through conventional means. It's as if nature has provided a secret passage through every wall, no matter how solid it appears. Perhaps our most unsettling quantum fact concerns the nature of nothingness itself. We typically think of empty space as truly empty, a perfect void containing absolutely nothing. But quantum physics reveals that even the vacuum of space seethes with invisible activity. What we call empty isn't empty at all. It's filled with a restless sea of energy fluctuations. These vacuum fluctuations arise from the uncertainty principle, which states that you can never pin down both the energy of a system and the time it takes to measure that energy with perfect precision. This means that even in supposedly empty space, energy can briefly appear out of nowhere, creating pairs of particles that flash into existence and then annihilate each other almost instantly. These virtual, as they're called, normally particles, remain invisible and undetectable, but under certain circumstances their effects become measurable. If you place two metal plates extremely close together in a vacuum, these quantum fluctuations create a tiny but detectable force that pushes the plates together. This Casimir effect demonstrates that the vacuum isn't passive emptiness, but an active participant in the physics of our universe. Some scientists speculate that these vacuum fluctuations might even explain one of cosmology's greatest mysteries: the dark energy that appears to be accelerating the expansion of our universe might arise from the quantum properties of empty space itself. If true, it would mean that nothingness is not only something, but the dominant force shaping the evolution of the entire cosmos. Now we encounter perhaps the most philosophically challenging aspect of quantum physics. When quantum systems exist in superposition, embodying multiple possibilities simultaneously, what determines which single outcome we observe when we make a measurement? This question has puzzled physicists for nearly a century and spawned numerous competing interpretations. The traditional Copenhagen interpretation, developed by pioneers like Niels Bohr, suggests that quantum systems simply don't have definite properties before measurement. The act of observation doesn't reveal a pre-existing reality. It actually creates that reality by forcing the system to choose from its range of possibilities. This view treats measurement as a fundamental aspect of nature, not merely a human activity. But this interpretation troubles many scientists and philosophers. If observation is so crucial, what exactly counts as an observer? Does it require consciousness? Or can any interaction with the environment trigger the collapse from possibility to actuality? The boundaries between observer and observed become surprisingly fuzzy when examined closely. An alternative interpretation proposes something even more radical. Perhaps the wave function never collapses at all. Instead, every possible outcome actually occurs, but in separate parallel universes that split off from each other at every quantum measurement. In this many worlds view, there are countless versions of you experiencing every possible result of every quantum event. You simply find yourself in one particular branch of an infinitely branching tree of realities. This interpretation eliminates the mystery of wave function collapse by suggesting it never happens. But it comes at the cost of an unimaginably vast multiverse, where every possibility is equally real. Somewhere, in some parallel universe, every quantum coin flip landed differently. Every radioactive atom decayed at a different moment, and every quantum measurement yielded a different result. Other interpretations attempt different solutions to this measurement puzzle. Some propose that the wave function represents our knowledge rather than physical reality itself. Others suggest that consciousness plays a special role in collapsing possibilities into actualities. Still, Others argue that the environment naturally selects classical behavior from quantum possibilities through a process called decoherence. What's remarkable is that despite these fundamental disagreements about what quantum mechanics actually means, all interpretations make identical predictions about experimental outcomes. The mathematics works perfectly regardless of which philosophical framework you prefer. Nature seems content to remain mysterious about her deepest operations while still revealing her patterns to careful observation. As you rest tonight, consider this beautiful paradox at the heart of our understanding. The most successful theory in the history of science, one that enables technologies from lasers to computer chips, remains fundamentally mysterious in its interpretation. We can predict quantum behavior with incredible precision, yet we still debate what that behavior actually represents about the nature of reality itself. Perhaps this uncertainty is not a flaw in our knowledge, but a feature of the universe itself. Maybe reality at its deepest level truly is probabilistic, fundamentally open-ended, resistant to being pinned down too precisely. In a strange way, this quantum indeterminacy might be what allows for novelty, creativity, and genuine surprise in a universe that might otherwise be completely predictable. The quantum world invites us to embrace a more nuanced relationship with knowledge itself. Instead of demanding absolute certainty, we can learn to find beauty in probability clouds and meaning in mathematical relationships that describe the likelihood of various possibilities. We can appreciate a universe subtle enough to be both knowable and mysterious, predictable and surprising, solid and ethereal, all at once. These quantum insights don't diminish the wonder of existence. They amplify it immeasurably. Every atom in your body, every photon reaching your eyes, every electrical impulse in your brain participates in this cosmic dance of probability and possibility. You are not separate from the quantum realm. You are woven from its very fabric, a conscious pattern emerging from the interplay of countless quantum interactions. Our next captivating fact takes us into one of the most mysterious territories of quantum physics, where particles become eternally linked in ways that seem to defy the very structure of space and time. This phenomenon, called quantum entanglement, creates connections between particles that persist regardless of the distance separating them, leading Einstein to famously dismiss it as spooky action at a distance. Imagine creating two particles that interact in such a way that their properties become fundamentally intertwined. Once entangled, these particles share a bizarre relationship where measuring one instantly determines the state of its partner, even if they're separated by entire galaxies. This isn't simply a matter of the particles carrying predetermined information, like two coins that were sorted before being sent to opposite ends of the universe. The reality is far stranger. Before measurement, neither particle possesses a definite state. They exist in a shared quantum limbo, a ghostly superposition where all possibilities remain equally real. Only when you observe one particle does the entire system snap into a specific configuration, with both particles simultaneously adopting complementary properties. This instantaneous correlation appears to violate one of the most sacred principles of physics, that nothing can travel faster than light. Yet countless experiments have confirmed that entangled particles do indeed respond to each other instantaneously, regardless of the distance between them. The connection isn't mediated by any signal or force traveling through space. Instead, the particles seem to share a single, distributed identity that transcends our ordinary concepts of locality. What makes this even more remarkable is that you cannot use entanglement to send messages faster than light. The results of measuring either particle are fundamentally random, so there's no way to encode information in the outcomes. It's as if the universe has found a way to maintain these mysterious connections while still preserving causality and preventing paradoxes. Scientists have now demonstrated entanglement over distances of hundreds of miles using satellites, and the effect shows no signs of weakening with separation. Some researchers speculate that entanglement might be a fundamental feature of space-time itself, perhaps even the mechanism that weaves the fabric of reality together at the deepest level. Moving deeper into quantum strangeness, we encounter another fact that challenges our intuitive understanding of time and causality. Certain quantum experiments suggest that the act of measurement can retroactively determine what happened in the past, as if the future reaches backward to influence earlier events. These delayed choice experiments begin with the familiar setup of particles passing through barriers with multiple openings. But instead of deciding in advance whether to measure which path each particle takes, experimenters wait until after the particle has presumably made its choice. Only then do they randomly decide whether to observe the path information or allow the particle to maintain its wave-like behavior. The astonishing result is that the particle's behavior matches whatever choice the experimenters make, even though that choice occurs after the particle has already passed through the apparatus. If they decide to measure the path, the particle behaves as if it went through a single opening. If they choose not to measure, it creates interference patterns, as if it traveled through multiple paths simultaneously. This temporal strangeness doesn't allow for science fiction scenarios of changing the past or sending information backward through time. Instead, it suggests that quantum systems don't commit to definite histories until all the relevant information has been gathered. The universe seems to maintain a kind of cosmic accounting system where final outcomes aren't tallied until every measurement has been completed. Some interpretations propose that time itself might be more flexible at quantum scales than our everyday experience suggests. Rather than a rigid sequence of cause and effect, quantum events might exist in a more fluid temporal relationship, where future measurements help determine past states. It's as if the universe keeps its books in pencil rather than ink, always ready to revise earlier entries based on later developments. Another remarkable quantum fact reveals that particles can exhibit properties that seem to change depending on how you measure them. This isn't simply a matter of measurement disturbing the system, but something more fundamental about the nature of quantum properties themselves. Consider the quantum property called spin, which has no direct analogy in our macroscopic world. When you measure a particle's spin along any particular direction, you'll always get one of two definite results. But here's the puzzle. If you measure the same particle's spin along a different direction immediately afterward, the results seem completely random, showing no correlation with the first measurement. This suggests that quantum particles don't possess all their properties simultaneously, in the way we might expect. Instead, the act of measuring one property seems to make others genuinely indefinite, not merely unknown. It's as if asking one question about a quantum system erases the answers to certain other questions, forcing the particle to exist in a state of controlled ignorance about itself. This complementarity principle extends far beyond spin measurements. Position and momentum, energy and time, and many other pairs of properties exhibit similar relationships where precise knowledge of one necessarily implies uncertainty about its partner. The universe appears to have built-in limits on how much we can know about any quantum system simultaneously. These limitations aren't technological hurdles to be overcome with better instruments, but fundamental features of reality itself. Nature seems to have adopted a policy of strategic ambiguity, revealing some information while carefully concealing other details. This cosmic discretion might actually be essential for the universe to function as it does, preventing the kind of logical paradoxes that could arise if all information were simultaneously accessible. Perhaps one of the most beautiful quantum facts concerns the role that information itself plays in determining physical outcomes. In many quantum experiments, what matters isn't the physical process of measurement, but whether the information exists in principle to distinguish between different possibilities. Quantum eraser experiments demonstrate this principle elegantly. Scientists can mark particles in such a way that their paths could theoretically be determined, which eliminates interference effects even if no one actually looks at the marking. But if the marking information is subsequently erased, making it impossible even in principle to determine which path was taken, the interference patterns mysteriously reappear. This suggests that the universe operates according to an information-theoretic logic, where the mere existence of distinguishing information, regardless of whether anyone accesses it, affects physical outcomes. It's as if reality maintains a strict accounting system, where what could be known is just as important as what is actually known. Some physicists propose that information might be more fundamental than matter and energy, that the universe at its deepest level consists of pure information, processing through space. In this view, particles rather than substance moving, forces, and even space-time itself might emerge from underlying patterns of information flow and transformation. This information-centric perspective offers intriguing possibilities for understanding other mysteries of physics. If information is indeed fundamental, it might provide clues for unifying quantum mechanics with gravity, or for understanding how consciousness relates to physical processes. The idea that reality might be computational at its core resonates with both ancient philosophical traditions and cutting-edge scientific speculation. As these quantum facts accumulate, they paint a picture of a universe far more subtle and interconnected than our everyday experience suggests. The boundaries between observer and observed, between cause and effect, between past and future, all become softer and more negotiable at quantum scales. What emerges is not chaos, but a deeper kind of order based on probability, information, and relationship, rather than simple mechanical causation. These insights invite us to reconsider our place in the cosmic scheme. Rather than being passive observers of an objective reality unfolding around us, we appear to be active participants in an ongoing creative process where consciousness, measurement, and physical reality interweave in ways we're still struggling to understand. The quantum world doesn't demand that we abandon logic or embrace mysticism, but it does ask us to expand our notion of what logical consistency might look like in a truly fundamental description of nature. Perhaps the deepest lesson of quantum physics is that reality is both stranger and more beautiful than we ever imagined, operating according to principles subtle enough to accommodate both scientific precision and genuine mystery. As you drift toward rest tonight, surrounded by this quantum tapestry of possibility and connection, remember that you are not separate from these phenomena, but intimately woven into them. Every breath you take, every thought that crosses your mind, every sensation you experience emerges from the same probabilistic dance that governs particles in laboratories around the world. In this quantum realm, where we've been exploring, there's another mesmerizing fact that reveals how the universe handles one of its most fundamental currencies, energy, itself. You might assume that particles can possess any amount of energy, smoothly transitioning from one level to another like a dimmer switch, gradually brightening a room. But the quantum world operates more like a staircase than a ramp, with energy existing only in specific allowed steps. This quantization of energy becomes beautifully apparent when we examine atoms, those tiny building blocks that compose everything around you. Within each atom, electrons don't orbit the nucleus like miniature planets, following any path they choose. Instead, they occupy very specific energy levels, like guests who can only stay on certain floors of a cosmic hotel, never in the spaces between. When an electron absorbs just the right amount of energy, it can leap from one level to a higher one, but it cannot linger anywhere in between. Similarly to a lower level releases energy, it drops down when it quantum jump, a single emitting a photon with precisely the energy difference between those levels. This is why different elements produce distinctive colors when heated, each atom's unique energy staircase creating its own signature pattern of light. This granular nature of energy has profound implications for how atoms remain stable. In a classical world, electrons would gradually lose energy and spiral into the nucleus, causing all matter to collapse. But quantum mechanics prevents this catastrophe through the uncertainty principle. An electron confined too closely to the nucleus would have such a precisely known position that its momentum would become wildly uncertain, requiring enormous energy. Nature finds a compromise, settling electrons into stable probability clouds that balance these competing demands. Our next remarkable quantum fact ventures into territory that seems to belong more in philosophy than physics. The quantum world appears to be fundamentally indeterministic, not because but because complete information may not exist. When a radioactive atom decides a particle chooses its to decay, when spin direction, when a photon selects its path through the outcome appears a beam splitter, to be genuinely random, rather than merely unpredictable. This quantum randomness differs qualitatively from the apparent randomness we encounter in daily life. When you flip a coin, the outcome seems random only because you cannot track all the relevant variables. The exact force of your thumb, air resistance, the coin's rotation rate, and countless other factors. In principle, these classical systems are deterministic, their outcomes fixed by initial conditions, even if those conditions are too complex to measure precisely. But quantum randomness appears to be different entirely. No amount of additional information about a quantum system allows you to predict with certainty which specific outcome will occur. The best you can do is calculate probabilities, and these probabilities appear to represent fundamental features of reality rather than limitations of human knowledge. This insight troubled many early quantum pioneers, including Einstein, who famously declared that God does not play dice with the universe. Yet decades of increasingly sophisticated experiments have confirmed that quantum events really do seem to involve genuine chance at the most fundamental level. The universe appears to be creative rather than merely computational, generating novelty through quantum processes that cannot be reduced to deterministic algorithms. Interestingly, this quantum indeterminacy doesn't lead to chaos. While individual quantum events are unpredictable, the statistical patterns they create are remarkably stable and precise. It's as if the universe maintains perfect order at the level of probabilities, while allowing complete freedom for individual outcomes. This balance between randomness and regularity might be essential for both the stability of physical law and the possibility of genuine novelty in natural processes. Moving deeper into quantum strangeness, we encounter a fact that reveals how measurement itself becomes a creative act rather than mere observation. In the classical world, measurement simply reveals properties that objects already possessed. But in quantum mechanics, measurement appears to participate in creating the very properties it detects. Consider a particle with an uncertain spin direction. Before measurement, it exists in a superposition of all possible spin orientations simultaneously. The act of measurement doesn't just reveal which direction the spin was pointing, it actually forces the particle to choose a specific direction from its cloud of possibilities. Different measurement approaches can elicit different sets of possible outcomes from the same quantum system. This participatory aspect of measurement has led some interpretations to suggest that consciousness plays a special role in quantum mechanics. If measurement requires an observer to collapse the wave function, and if observers are necessarily conscious beings, then consciousness might be fundamentally involved in determining physical reality. While this interpretation remains controversial, it highlights how quantum mechanics blurs the traditional boundary between subjective experience and objective physical processes. Other interpretations avoid this consciousness puzzle by suggesting that any interaction with the environment, conscious or not, can trigger the measurement process. In this view, quantum decoherence occurs naturally as systems become entangled with their surroundings, gradually losing their quantum coherence without requiring special intervention from conscious observers. Yet another approach proposes that measurement never actually occurs in the traditional sense. Instead, quantum systems continuously evolve according to their wave equations, with apparent measurement outcomes emerging from the observer's perspective within a vast multiverse of parallel realities. Each interpretation offers a different resolution to the measurement puzzle, but all acknowledge that quantum mechanics has transformed measurement from passive observation into active participation in the creation of reality. Here's a quantum fact that reveals something profound about the nature of identity itself. In our everyday world, objects maintain their individuality even when they're identical. Two pennies might look exactly alike, but they remain distinct entities with separate histories and locations. You can always, in principle, keep track of which penny is which. But quantum particles of the same type are truly indistinguishable in a way that has no classical analog. Two electrons aren't just very similar, they're absolutely identical in every measurable property. More remarkably, quantum mechanics treats them as fundamentally interchangeable, meaning that swapping their positions doesn't create a different physical state, but rather the same state, described differently. This quantum indistinguishability leads to strange statistical behaviors that have no classical counterparts. When identical particles occupy the same quantum system, their wave functions must either remain unchanged when particles are swapped, or change only by acquiring a negative sign. This seemingly abstract mathematical requirement leads to two distinct classes of particles with dramatically different behaviors. Particles whose wave functions remain unchanged, called bosons, can same quantum state crowd together in the without restriction. This allows phenomena like laser light, where billions of photons coordinate their behavior, where entire collections of atoms merge into single quantum entities visible to the naked eye. Particles whose wave functions acquire a negative sign when swapped, called fermions, obey an exclusion principle that prevents any two from occupying the same quantum state, occupying identical quantum states. This fermionic antisocial behavior is responsible for the structure of atoms, the stability of matter, and even the existence of chemistry itself. Without the exclusion principle, electrons would all collapse into the lowest energy levels, making complex atomic structures impossible. The implications extend far beyond particle physics. Even more exotic stellar remnants, neutron stars, are supported by the exclusion principle operating among neutrons. In a sense, some of the most extreme objects in the universe owe their existence to quantum statistics that emerge from the fundamental in our next quantum distinguishability of particles. Revelation concerns that quantum systems the surprising ways can share information and coordinate their behaviors across vast distances. We've touched on entanglement, but there's an even more fundamental level at which quantum systems seem to communicate through what physicists call quantum fields. Every type of particle is associated with a field that permeates all of space. The electromagnetic field gives rise to photons. Electron fields create electrons, and quark fields manifest as quarks. These fields are not empty containers waiting to be filled, but dynamic entities that constantly fluctuate and interact with each other according to quantum principles. When particles interact, they're actually excitations in these underlying fields, exchanging energy and momentum through quantum field fluctuations. What we perceive as forces between particles emerge from the exchange of virtual particles, temporary excitations in quantum fields that mediate interactions before disappearing back into the vacuum. This field-theoretic picture reveals that apparently empty space is actually a bustling marketplace of quantum activity. Virtual particle pairs constantly pop into existence and annihilate each other, creating a quantum foam that affects the properties of real particles passing through it. These vacuum fluctuations can be detected through subtle effects on atomic energy levels and through forces between closely spaced conducting plates. The quantum field perspective also provides elegant explanations for particle creation and destruction in high-energy processes. When sufficient energy is concentrated in a small region, it can excite quantum fields enough to produce real particles from what appeared to be empty space. This process operates in reverse as well, with particles annihilating back into field energy under appropriate conditions. Some theorists propose that quantum fields might provide the foundation for unifying all fundamental forces and particles into a single theoretical framework. If successful, such theories would reveal that the apparent diversity of natural phenomena emerges from various excitation patterns in a small number of underlying quantum fields. As we continue exploring these quantum mysteries, we encounter a fact that challenges our basic assumptions about the nature of space and time themselves, the smallest possible. Quantum mechanics suggests that at scales, the smooth fabric of space-time predicted by Einstein's relativity might give way to a discrete, granular structure built from quantum units of space and time. At distances 10 to the negative 35th meters, smaller than the Planck length, about the quantum fluctuations of space-time itself become so large that the classical notion of smooth geometry breaks down entirely. Similarly, at time intervals shorter than the Planck time, about 10 to the minus 43 seconds, the concept of continuous temporal flow might cease to apply. Some approaches to quantum gravity propose that space-time emerges from more fundamental quantum processes, much like temperature emerges from the motion of individual molecules. In these theories, what we experience as the dimensions of space and the flow of time might be statistical approximations that apply only at scales much larger than the quantum realm. This possibility has profound implications for our understanding of causality, locality, and the nature of physical reality itself. If space-time is not fundamental but emergent, then some of the deepest puzzles in physics might find resolution through quantum processes that operate according to logic quite different from our macroscopic intuitions. The relationship between quantum mechanics and gravity remains one of the greatest unsolved problems in physics. Neither quantum field theory nor general relativity seems capable of describing what happens when quantum effects and gravitational effects become equally important, such as in the cores of black holes or during the first moments after the Big Bang. Various approaches to quantum gravity, from string theory to loop quantum gravity to emergent gravity theories, offer different perspectives on how this unification might be achieved. While none has yet succeeded completely, each contributes insights that deepen our appreciation for the subtle and the structure relationships between quantum phenomena of space-time itself. Perhaps one of the most beautiful quantum facts concerns the role that symmetry plays in determining the laws of physics. Quantum systems exhibit various types of symmetries, mathematical transformations that leave physical outcomes unchanged, and these symmetries turn out to be intimately connected with conservation laws and the fundamental forces of nature. When a quantum system remains unchanged under spatial rotations, this symmetry corresponds to conservation of angular momentum. Symmetry under time translation leads to energy conservation, while symmetry under spatial translation corresponds to momentum conservation. These connections between symmetries and conservation laws, formalized in Noether's theorem, reveal deep mathematical harmonies underlying physical processes. More exotic symmetries in quantum field theory lead to the existence of fundamental forces and the properties of elementary particles. The electromagnetic force emerges from gauge the electron symmetry in field, while the strong nuclear force arises from color symmetry among quarks. Even the masses of particles can be understood as consequences of spontaneous symmetry breaking, where quantum fields adopt configurations that hide their underlying symmetrical structure. These symmetry principles provide powerful constraints that guide physicists in constructing new theories and predicting undiscovered phenomena. Many of the greatest advances in fundamental physics have come from recognizing previously hidden symmetries or understanding how apparent asymmetries emerge from deeper symmetrical structures. The interplay between symmetry and quantum mechanics continues to reveal new aspects of nature's underlying mathematical architecture. As physicists probe deeper into the quantum realm, they consistently find that aesthetic principles like elegance, symmetry, and mathematical beauty serve as reliable guides toward truth about the physical world. As your mind drifts through these quantum contemplations, consider how each of these facts represents not just an isolated curiosity, but part of a vast interconnected tapestry of relationships that govern everything from the stability of atoms to the evolution of galaxies. The quantum world doesn't exist separately from your daily experience. It forms the invisible foundation upon which all familiar phenomena rest. Every sensation you experience, every thought that forms in your consciousness, every biological process that sustains your life emerges from quantum mechanical processes operating at scales far too small to perceive directly. Yet their influence permeates every aspect of existence, creating the stable patterns we recognize as matter, energy, space, and time. The quantum realm holds another breathtaking secret about how the universe maintains its delicate balance between order and chaos. Deep within atomic nuclei, quantum mechanics governs processes so fundamental that without them, stars would never shine, and life itself could never have emerged. Nuclear fusion, the process that powers our sun and every other star, relies entirely on quantum tunneling to overcome what should be an impossible barrier. Inside stellar cores, hydrogen nuclei carry positive electrical charges that naturally repel each other with tremendous force. According to classical physics, These particles simply don't possess enough energy to overcome their mutual repulsion and merge together. The temperatures and pressures inside stars, while extreme by earthly standards, fall far short of what would be needed to force fusion through brute force alone. Yet fusion happens continuously, flooding the universe with light and energy. The secret lies in quantum tunneling, where particles can slip through energy barriers that should completely stop them. The wave-like nature of matter allows a tiny fraction of hydrogen nuclei to tunnel through the electrical barrier and fuse together, releasing energy in the process. While any probability the four-individual collision is vanishingly small, the sheer number of particles in a star ensures that fusion proceeds at exactly the right rate to sustain stellar burning for billions of years. This same quantum principle operates in radioactive decay, where particles trapped inside atomic nuclei can tunnel out despite lacking sufficient energy to escape classically. The randomness of quantum tunneling explains why radioactive decay follows statistical patterns rather than predictable schedules. You cannot predict exactly when any particular atom will decay, but you can calculate precisely how long it takes for half of any sample to transform. Moving from the cosmic to the intimate, quantum mechanics reveals surprising connections between the physics of the very small and the biology of living systems. For decades, scientists assumed that quantum effects would be too fragile to survive in the warm, wet, noisy environment inside living cells. But recent discoveries suggest that evolution may have learned to harness quantum phenomena for some of life's most essential processes. Consider the miracle of photosynthesis, where plants convert sunlight into chemical energy with remarkable efficiency. When a photon strikes a chlorophyll molecule, it creates an excited state that must transfer its energy to a reaction center where it can be captured and stored. Classical physics would expect this energy to hop randomly from molecule to molecule, losing much of its power along the way. But experiments hint at something far more elegant. The energy appears to explore multiple pathways simultaneously through quantum coherence, allowing it to find the most efficient route to its destination. It's as if the excitation exists in a superposition of all possible paths until it collapses into the optimal one. This quantum-assisted navigation helps explain why photosynthesis achieves such impressive efficiency rates, far better than our best artificial solar cells. Similar quantum effects might operate in other biological systems. Some birds appear to use quantum entanglement in specialized proteins within their eyes to detect Earth's magnetic field for navigation. The quantum compass in their visual system could provide them with a magnetic sense that overlays their normal vision, helping them find their way across thousands of miles of open ocean. Even your sense of smell might involve quantum mechanics. One theory suggests that odor receptors don't just detect molecular shapes, but also sense the vibrational frequencies of molecules through quantum tunneling effects. This could explain why molecules with similar shapes sometimes smell completely different, while structurally distinct molecules can produce identical scents. Here's a quantum fact that illuminates the profound difference between quantum and classical descriptions of physical systems. In our everyday world, systems possess definite properties, whether we observe them or not. A spinning top has a specific orientation, a moving car has a particular velocity, and a coin shows either heads or tails, even when no one looks at it. But quantum systems refuse to conform to this classical picture. Before measurement, they exist in superpositions where multiple contradictory properties coexist simultaneously. A quantum particle doesn't have a definite position or momentum. Instead, It embodies a probability distribution over all possible values of these quantities. The mathematics of quantum mechanics represents these superpositions through wave functions, complex valued functions that encode everything knowable about a quantum system. The wave function itself cannot be directly observed, but its squared magnitude gives the probability of finding specific measurement outcomes. When a measurement occurs, the wave function appears to collapse from its spread of possibilities into a single, definite result. This collapse happens instantaneously and completely, regardless of how large or complex the quantum system might be. One moment the particle exists everywhere it could possibly be. The next moment it has committed to a single location. Different interpretations of quantum mechanics offer varying explanations for this collapse process. The Copenhagen interpretation treats collapse as a fundamental feature of measurement, while many worlds theories suggest that all possible outcomes actually occur in parallel universes. Objective collapse models propose that wave functions spontaneously collapse due to random processes, while informational interpretations focus on the role of knowledge and observation in determining outcomes. Despite these interpretive differences, all approaches agree that quantum mechanics has fundamentally transformed our understanding of physical reality. Properties like position, momentum, and energy are no longer viewed as intrinsic attributes of particles, but as emergent features that crystallize through interactions with measuring devices or environments. The quantum world also reveals deep connections between information and physical processes that have no classical analogs. In quantum systems, the mere existence of information about a system's state can affect its physical behavior, even if no one actually accesses that information. This suggests that information itself might be as fundamental as matter and energy in determining how the universe operates. Quantum computers exploit these informational aspects of quantum mechanics to perform calculations that would be impossible for classical machines. Instead of processing information through sequences of definite states, quantum computers manipulate superpositions and entangled states to explore vast numbers of possibilities simultaneously. A classical computer bit exists in either a 0 or 1 state, but a quantum bit or qubit can exist in superpositions of both states at once. Multiple qubits can become entangled, creating correlations that allow quantum algorithms to solve certain problems exponentially faster than any classical approach. These quantum computational advantages don't apply to all problems, but for specific applications like factoring large numbers, simulating quantum systems, or searching through vast databases, quantum computers offer revolutionary speed-ups. The challenge lies in maintaining quantum coherence long enough to complete useful calculations, as quantum states are extremely fragile and easily disrupted by environmental interference. Scientists have developed sophisticated error correction schemes that use multiple physical qubits to protect single logical qubits from decoherence. These techniques borrow ideas from classical error correction, but must deal with uniquely quantum challenges like the no-cloning theorem, which prevents direct copying of quantum states. As quantum computing technology matures, it promises to transform fields ranging from cryptography to drug discovery to artificial intelligence. Some encryption methods that currently protect internet communications could become vulnerable to quantum attacks, spurring development of new cryptographic techniques based on quantum principles. The quantum realm continues to surprise us with phenomena that challenge our deepest assumptions about the nature of time itself. Certain quantum experiments suggest that the temporal order of events might not always be definite. leading to scenarios where cause and effect relationships become ambiguous. In quantum systems, events can occur in superpositions of different temporal orders, where it becomes meaningless to ask which happened first. This temporal indefiniteness doesn't violate causality in the classical sense, but it does reveal that time might be more flexible at quantum scales than our everyday experience suggests. As we reach the end of our quantum journey tonight, perhaps you're already drifting between the worlds of waking and sleeping, much like the particles we've explored that exist between definite states. We've wandered through a universe far stranger and more beautiful than our everyday senses reveal, where reality shimmers with possibility until the moment we choose to look. From energy arriving in discrete packets to particles tunneling through impossible barriers, from entangled pairs sharing instant connections across cosmic distances to the creative act of measurement itself. Quantum physics has shown us that the universe operates on principles both precise and mysterious. Sweet dreams, and may your rest be filled with the gentle hum of quantum possibilities.